Hey there. I recently multi-threaded the render of my Vulkan game engine project, and I wanted to talk a little bit about it because I found it interesting, and I like talking about interesting things. So this is a simple breakdown of the game logic render loop prior to this change. This is a fairly naive approach, and we're going to break it down a bit. So this is a timeline from left to right as time progresses. We got our game logic occurring. We got our CPU side prep for frame render. We've got the actual GPU side rendering of the frame. And here red we have the time that the CPU is spending not running the game or engine because the game is targeting a specific number of logic ticks per second, which while that can be changed, of course, at runtime and everything, generally speaking, you don't want that to be completely unbounded, so there's going to be some sort of sleeping occurring here. So this is game logic happens, CPU prepares stuff for the GPU, GPU renders while the next frame starts logic. And that occurs over and over and over again. You get your frame at the end of each of these yellow bits. This is very simplistic and high level, but this is roughly what was happening. It's been changed to this now, where the render prep is now occurring concurrently to the ability for the game to be running game logic. So at the end of each game logic tick, then the render prep, the CPU side render prep can begin, but the main logic is free to do something else. In this case, because it's being restricted to a specific refresh rate, there's a specific rate of ticks, it's sleeping, but it could be running game logic here. So game logic occurs, and then the render prep happens concurrently, and then the render starts on the GPU side. Now, this doesn't seem like that big of a deal, but it actually has some pretty severe consequences. So here's an example of the old original non-concurrent, non-multi-threaded rendering approach in the case of the CPU not quite being up to the task of handling the current game scene. So this is the sort of case where the game starts running slowly because the computer you're running on simply can't keep up with maybe physics or complex AI or whatever was going on in the scene. So you see our game logic is taking a long time here, and we're not sleeping at all. We've bottomed out we're running either right on the edge of we're just barely making our tick rate, or we're running too slow and we're missing tick rate. So we're running slower than we're expecting to be. Either way, we're never sleeping, right? The CPU is straight up always working on something. And so now, this chunk of time that's being spent on render prep means a bit more, because here, this is the render thread. This is the new system where we were. This is assuming we're taking the same amount of time to run game logic as we did before, where we were starting to slow down. But now, because the render prep is occurring concurrently, potentially on another thread, potentially on another core, now we have this space here that, if assuming we were just barely making our deadlines for when the game ticks were supposed to be occurring, now we have extra headroom that we know we're definitely going to hit that. And if we're not, we have extra headroom to account for that and sleep for a less amount of time to make sure we hit that. So it offloads more of the work off of the game logic and allows higher potential throughput. But this is a very naive way of looking at the actual render loop of a game, because the blue and yellow parts, our render prep and our actual rendering on the GPU side, is limited in how often we're allowed to do that in most situations by the driver OS and monitor, because monitors have a set refresh rate, or they have FreeSync or G-Sync, at which point their refresh rate is variable. And unless you are going gung-ho and just rendering as fast as possible and getting tearing as a result, which is something that my engine does support, because that's how I prefer to play games, because latency, and there's a whole big latency thing to talk about here. But unless you're doing that, you're trying to render just ahead of when how often you're allowed to render is being restricted by how often the monitor is refreshing, which might either be static, at which point now in this original situation where the game logic occurs and then a render occurs and then more game logic occurs, then another render occurs, then more game logic occurs, then another render occurs. Now you're assuming that the tick rate of your game logic is matching the refresh rate of the monitor, which just doesn't work out in practice. And then you add in FreeSync and G-Sync monitors into the mix, where now the refresh rate of the monitor changes on the fly, and now the driver is expecting you to handle that. This gets way messy really quickly, and you end up either, if you're using FIFO presentation, you end up just like, the way my engine works is it's currently configured to use a it's called target FPS right now. I need to change the name of that. Right now it's 90 hertz is the internal game logic loop, is 90 hertz. My monitor is 75 hertz. So in my case, when using FIFO rendering, which is one of the approaches for doing VSync, and is the only thing I can rely on actually being present, that as in like that is the guaranteed to be their supported mode. In that case, if I'm running my internal game logic, like the green is occurring 90 times a second, but I'm only allowed to do the yellow 75 times per second. It ends up overwhelming the FIFO queue, and then you get horrible latency issues, and all sorts of fun stuff occurs. So, by disengaging that, now the game logic is completely separate. This UI, this mockup is still showing it being sequential, but the game logic can occur here multiple times and then a render occur, or a render can occur multiple times within the same game logic. It's kinder to the situations that the driver is expecting me to be able to handle. So let's look at some code, because I feel like I didn't explain that very well, and this is not like a super complicated approach to doing any sort of multi-thread rendering. This is more of me just trying to not like do as horribly, because technically Vulkan provides a lot of tools for you to be able to do interactions with the GPU API concurrently in a lot of different interesting ways, and I'm doing none of that. So this is a lot more of a traditional, like, we have a render thread now, which I feel like if you've ever played like a source engine game, like there's a checkbox in the settings for that, and that's like super old DirectX 9 and OpenGL renderer. So like, this is nothing super complicated or groundbreaking, but it's interesting to think about and talk about. So the render, this is the main game loop right here. Yeah, this is the main game loop, and we're not going to like dig into this, but this is the green. All the logic that's inside this brace, set of braces is the green, and then here's the actual the logic for doing sleeping and stuff and making sure that like it's actually hitting the target tick rate, and if not, sleep for less time and all that sort of stuff, or loudly complain over standard out that it can't keep up, which this printing here would be when that green is taking up all of the bar and the CPU simply can't keep up with the game scene, and now game time is just slowing. It's all sorts of fun stuff. But we've got absolutely no render logic in here. There used to be render logic in here. There is not. Instead, what we have is this render thread. So here's the render thread in its entirety. This is all the render thread. And this runs on a separate thread, and it's in charge of all the rendering processes. So whenever the game logic reaches the end of processing a current tick, it takes and sends what's known as a render package across a channel over to the render thread. Now this package contains a snapshot and our UBO. Now UBO is just a render thing that contains stuff like camera position and stuff like that. Well, it's a lot more complicated than just camera position. There's a few 4x4 matrices in there with some math that I don't fully grasp, but it's fun stuff. But the snapshot is this, if we go pull up the snapshot. So the scene snapshot, this slivers stuff is me starting to work on UI stuff, but I wanted to talk about this because this is interesting. The scene snapshot contains all the information that the GPU needs to know about the scene in that exact moment in order to be able to render it. So primarily, this is entirely unused. It's just mesh information. So the meshes is this really efficient, really cheap to build representation of all the meshes in the current scene that is built each frame as the entity system runs the logic for each entity. And this information, this contains no actual mesh information. This is just the information that the GPU needs to know in order to draw the correct number of meshes of the correct types in the correct locations with the correct additional data in order to draw all the meshes in the scene. Because all the meshes are uploaded at the beginning, and then their mesh data is reused because instance drawing. But this is really a really efficient representation that's really, and you're looking at all of the code for it, that's really efficient to build CPU sidewise as the entity system ticks each entity and then adds its mesh to this information. But this is just a few mem copies away from being in GPU memory in the correct representation to be really efficient to render. So, if we go back here to the main thread, here we got scene entities tick all, and we're passing in that meshes information mutably by mutable reference, so that the entity system goes through and as it ticks each entity, adds its information to this representation of the scene that's really cheap to build, right? So it's not building much data here, and it's really efficient to copy in GPU memory. And then we package that up and send it to the render thread. The render thread has some nested loops. Basically, every time it's got this main render loop, and every time it spins that loop, it goes and tries to read all of the messages that are on that channel, handling different situations like regenerating the swap chain if the window size changed or stuff like that. But if it gets a render package, it puts that in this variable, maybe package, because it may or may not be a package. And if there's already one there, it sends that existing package back to the main thread. Because while the scene snapshot data is very cheap to build, it requires a few allocations. So we do those allocations up front, and then we have one or more of those being constantly recycled back and forth between the two threads, so we never have to do those allocations ever again. So it's really cheap. There's some things I need to look into in the physics engine I'm using, but all of my code here, no allocations under normal operating conditions, like normal gameplay wise. Well, no, the entity system has a specific spot where it has to allocate stuff, and I'm not happy about it, and I'm going to be changing that API as soon as I can figure out a better way to do it. Anyway, so every render loop, it goes and checks to see if it gets an updated package. If it does, it puts that package in as the new package, and then sends back any old package. So at the beginning of each loop, it makes sure it has the current, most up-to-date snapshot of the scene's representation. Because again, multiple game ticks could occur between renders. So it has to make sure that it has the most up-to-date representation of the scene that it has been handed. So then we say if we have a current scene snapshot, we have a package with the snapshot and the UBO. We attempt to draw the frame, and that goes off into all the Vulkan code and does all sorts of render stuff. And then if we check to see if we need to regenerate the swap chain because the window changed, but the main thread hasn't told us about it yet, so we need to take care of that, blah, blah, blah. And if we did correctly, completely render, set up to render a thread, frame, then we take the snapshot that we just rendered from, right, that representation of the scene, and we send it back to the main thread. So now the render thread no longer has one, which is why it's the maybe package. So that means that the render thread is never going to re-render the same snapshot of the scene multiple times. We avoid doing unnecessary allocations by recycling these snapshots. And if there are multiple logic ticks between renderings, then it will only ever render the most up-to-date version of the scene. And all of that is extremely efficient, and of course, like all of the snapshot information, we go in here to draw frame, and then we come in here to record frame commands. Here's the actual where is it? Yeah, here we go. Here's all of the information. Here's all of the logic for like copying that scene representation into GPU memory. Like, here's a mem copy. Like there's like, we got by model, right? So there's like, it does like maybe 3 or 4 mem copies, and the entire scene representation is in GPU memory, and I love it. So yeah, this gets into a lot more latency based stuff as well. In some specific circumstances, it can improve latency by like a frame, I think, simply because it always renders the most up to date version of the scene. Whereas, yeah, I was trying to do some clever stuff in the single-threaded world prior to doing this, to get some of the benefits of this multi-threaded thing, but it's better to have it like proper, and that's what I have now. This was fairly easy, if a bit tedious to do. Technically, I'm using an API, where is it? In a way that's not entirely, I'm not entirely supposed to. So somewhere in here there's, I'm using SDL2 for windowing and input. And it's not explicitly thread safe, but the documentation says just don't use the video module from more than one thread concurrently. And that's it. So because the way the Rust bindings for SDL2 work. All of the stuff in the video subsystem are methods hanging off of the window object. And this is not clonable or copyable. So you have a window and you can only access it from that window object, and you cannot create multiple copies of that window object. So because once I pass that to the render thread, I can't access it anymore. The borrow checker, even though this is a C API, right? This is one of the wonders of Rust, and this is definitely something that the people wrapping SDL2 thought about. But because of the wonders of Rust, even though this is a C API that I'm interacting with, and there are places where I've done this sort of thing with Vulkan APIs because I'm using the raw C Vulkan API. It entirely prevents any sort of issues with concurrently accessing this. So moving this code into being multi-threaded, aware, and avoiding concurrency issues with libraries was like not a problem, which is awesome. And that's just like one of the things that came into practice on that specific topic. So yeah, it's multi-threaded rendering, technically. Multi-threaded engine-ish. There are engines out there, a lot of them in Rust, that have like entity systems that are able to like figure out dependencies and figure like, oh, these entities don't rely on these entities, so we can run them on separate threads and like concurrently do game logic updates, which is really cool. But that's not what I'm doing. So, like I said, this is fairly simple of a system, not new in any way, shape, or form. Just like doing rendering on a separate thread and passing information back and forth. But yeah, I'm happy with it. I have a lot more latency-based stuff to fight with because drivers are annoying. But yeah, pretty cool. I'm excited about continuing to work on this. I'm working on some UI stuff now, which is fun because I have to get 2D rendering up and running in this, which requires a lot of deep diving back into the internals of the renderer and dealing with some stuff that is less obvious, because the Vulkan API is honestly really, there's a lot of stuff you have to do top to bottom in order to get like one thing happening. So while the mesh rendering system is pretty complete at this point, I need to add texturing back into it. Yeah, I have to like go rebuild another render pass almost from scratch to do 2D rendering. But yeah, it's fun, cool stuff. Yeah, that's about it. Thanks for watching. Cheers.